Okay, we'll kick off. Thank you all for coming. It's really nice to be here. I haven't had the opportunity to speak at this conference before, but it seems pretty awesome. I thought the boat cruise was good. My name's Ben Stopford. I work at this company called Confluent. So that's the company that basically sits behind Apache Kafka, which is an open source streaming platform. We'll be talking a little bit about that today, on and off. And today, really, we're going to talk about the intersection between two different worlds. The world of kind of business systems, microservices, that sort of thing, and the world of stream processing, which really kind of comes from a very different area, a different stance, with a different set of requirements. But the two, when combined, are pretty interesting. Hopefully, you'll see that today. So when we build software on a kind of daily basis, we tend to have a couple of different masters. There's kind of this very obvious master, which is that we want to build features. So your users come to you and they say you want to build a report or maybe put something on a screen. These kind of things are very visceral. They're very obvious. This is why you go and sit at your desk in the morning and kind of write code. But at the same time, you also tend to think maybe more subtly about some other goals, things that make your software work, not just today, but also in the future. When we think about software lasting over time, we're not really thinking about those files sitting in GitHub on a file system, when obviously they could sit there indefinitely. We're thinking about their ability to evolve over time. And we actually do this intuitively all the time. Every time you write software, you're thinking about carefully modularizing your code so that it can be reused, making it understandable so that when you come back to it later, you can actually work out what it was supposed to do. Likewise, you'll do things like write tests, right? So whilst you might write tests to assert the behavior today, really the value of testing comes in the future. It's future-proofing your software. Same is true for continuous delivery, continuous integration. All of these practices are about kind of thinking about and preparing for the future. But when we think about software architecture, putting different pieces together to create a system, we actually don't tend to think about it in the same way. And we don't always think about it in the same way. So I think, for me, a lot of this talk is about trying to work out how to build systems that last. The systems that we can actually evolve in the same way that we evolve our code in our code base. So it's very much about this idea of evolution. Software and the systems we write evolving over time. So to take a slightly different tack, I wanted to talk a bit about stream processing. Anyone do stream processing today? Got a few. Okay. So, for very high level, this is kind of an example of a stream processing system. So, you probably all have a mobile phone in your pocket. Maybe it's an Apple one or a Google one or whatever. That's kind of a sort of canonical stream processing use case. And the reason is there's kind of like a billion phones out there. And they're all transmitting messages back to your various different providers or applications that you're using. So, if you're like Apple or Google, you'll be recording like every time somebody opens an application or every time the application crashes. And this creates a very sort of high throughput workload of actually very small messages, right? It's got lots and lots of small messages coming from lots of different handsets around the world. So how do you kind of deal with that kind of problem? Well, you'll probably use something like a streaming platform. So you'll put the data into Kafka. So Kafka's providing a buffer, which is going to buffer all that information up. And then the stream processing layer is something which allows you to perform a computation as these events arise. So let's say we want to do something very simple, like work out some statistics for how many people are using a certain application, we could sort of put those into HDFS or maybe some other file system, and then every so often we could kind of run a batch job over that and do the computation that we want to do. But typically we don't want to do those kind of batch computations because they're so slow. You'll get a result maybe once a day for these kind of workloads. So streaming is really about the idea that we want to be able to compute those kind of results as continuously as they happen. And when you the tool set that you use to address this kind of problem is slightly different. So it has a few elements. First, it has a high throughput messaging system. You need something that's going to scale out and something which is going to provide you high availability. The streaming layer itself is optimized to deal with this kind of problem. And that means, it needs to be able to compute incrementally, but also it needs to manage state. And one of the things that it actually does is it gives you the opportunity to create stateful stream processing nodes so that you can localize the state inside the stream processing node so that it can operate very efficiently. And then finally, you're typically, in this kind of architecture, you have some kind of serving layer which you'll attach a GUI to and query directly. You can actually query a stream processor directly if you want to also. Kafka Streams, for example, provides that interface. But here I've used Cassandra, which is another pattern that's pretty common. So let's take a little example. Imagine we have a number of users around the world who are just using their credit cards. And every time you use your credit card, you get an authorization attempt. And we're interested in finding potentially fraudulent activity. So we have our input into this particular computation is authorization attempts, people using their cards, and what comes out is this potential for a fraud. And we can do that very simply by, at a very sort of simple level, by counting the number of attempts in some particular amount of time. And this is expressed as, this is a thing called KSQL. It looks a bit like SQL in a database, as you can tell, except that it runs on a stream processing engine. So we're going to start with our input, a stream of authorization attempts. From there, we're going to create an output, a stream of potential fraud, possible fraud, fraudulent events. Then we're going to select the card number and then the count. And importantly, this is kind of where it differs from your standard database SQL. We're going to do that over, in this case, a 5-minute window. So that means that we're going to get a rolling average over that, a rolling computation over that 5-minute window. And then we're going to add a group by the card number, and then we're going to filter that based on a count of more than 3. So a very, very simple computation, which is going to run continuously. And that's kind of like a very canonical stream processing use case. So stream processing really is a tool for dealing with data in flight. So specifically manipulating it, joining different streams together, and adding computation on top of that. So what's this got to do with business applications, you might wonder? Well, today we tend to build ecosystems. Increasingly, we build these kind of ecosystems. So SOA has been around for a long time, well over a decade now. Microservices, which are in many ways a reinvention of SOA in the context of really evolution of hardware and software. Same kind of principles, and then things like event-driven architectures. But in all of these, what we're really doing is we're compartmentalizing our problem into specific concerns which match our domain. So here I'm going to keep using this retail context throughout this presentation. So we have an order service, and we have a customer service, and so customer service will obviously hold our record of customers, and the stock service will hold our inventory of what's inside our warehouse. And each of these services has a specific responsibility. It should be pretty obvious. So the problem with these kind of architectures tends to be around data. None of those patterns are actually particularly opinionated around data. Like SOA was always just like, well, if you need some information, you just go to a service and get it. And that kind of makes sense for a certain number of use cases. But anything that's more data-centric, it actually becomes quite difficult. So you can imagine, even in a retail context, if I have a set of these different services, data kind of is going to form into these islands, which in many ways makes sense. But a whole variety of these different services are going to need access to these core data sets. So they're going to need to have customer information and order information and the product catalog in order to do their work. So where this becomes a little bit more tricky is when we start to have slightly more data-intensive operations. Right, so if we're doing something like really simple, like displaying something on a dashboard, just like a lookup table, it's pretty simple. But as soon as we do something that's a little bit more data intensive, let's say we just have like a grid where you can scroll up and down, and in the background you're hitting a variety of different services, you don't have to scroll that fast before hitting all of these different services, particularly if you're doing a kind of join which involves accessing maybe orders and then payments and then customers. It becomes actually quite difficult to manage. You have to sort of think about batching and then caching things locally and then polling for new updates, et cetera, et cetera. So these kind of slightly more data-intensive operations turn out to be quite difficult to perform. So one very simple solution is just to have one big database. Actually, a lot of companies do this. Quite a lot of companies have some kind of central operational store. It's a tricky pattern to get right. Obviously, intuitively, it's kind of quite nice. It's like, oh, I've got all my services. I can just put all my data in a database. Everyone can access it. It sounds like it's going to make a lot of sense in a static sense. Like today, that will probably work. But what the pain that comes with a shared database is actually is this evolution thing. As each of these services changes over time, because they are independently deployable, they're typically going to be run by different teams. The database provides this relatively high coupling point, which makes it difficult to evolve. So databases provide this kind of very rich form of coupling. So what this kind of leads to is two different forces which compete in the design of the software that we build. So on one side, we're taught to encapsulate. We've all done this, right? We've all done our kind of OO modeling, et cetera, et cetera. And this kind of makes a lot of sense. So let's say we have a single sign-on service. It has an interface, nice, neat interface called authorize, and I have some business service which calls that. I use encapsulation to hide the state and behavior that sits inside my service. Makes a lot of sense. Nice, clean interface, not too much for people to couple to. I can basically change the internals of that without it being too much of a problem. All kind of makes a lot of sense. Loose coupling is good. The problem with data systems is they don't really have anything to do with encapsulation. In fact, they do exactly the opposite. A database does everything it can to make the data that it holds as easy for you to get at as possible. It actually provides this wonderful wealth of tooling which allows you to slice and dice data in a variety of different ways. In fact, you can often, you can reform it into different views. You can make it look completely different to the core data set. It's literally the antithesis of encapsulation. So if you can imagine like a service on the left-hand side, it has data on the inside, and it's doing its best to encapsulate that, to not expose it to the outside world. And the reason it's doing that is because it wants to be able to change. It wants to control over that, and it wants to limit the interface that it exposes. But a database does exactly the opposite. Right? It has some data inside. It actually provides amplifying contracts, which is richer than the data that it holds internally. So you kind of get this competition between these two different forces. On one side, encapsulation is encouraging you to limit your interface, so you reduce coupling. But then you have these data systems which are actually amplifying, providing an amplifying interface. And that's not to say data systems are bad. We need data systems. We need these amplifying interfaces because they do useful work. They allow us to introspect data, to build different types of data-centric problems for our users. So we actually need both of these things, but we have to understand how they sit in the systems that we build. So this leads to this kind of dichotomy. On one side, data systems are very much about exposing data, and that allows you to get on with your job today. Whereas services are really about hiding it, which is about protecting yourself against potential coupling in the future, which allows your system to evolve. So these two forces basically fight against one another in the systems that we build. So it's said quite sensibly, really actually mostly from experience, that microservices shouldn't share a database. Who's heard this? Show of hands. Ooh, very knowledgeable crowd, I like it. So Sam Newman talks about it in his book. It's talked about on the internet all over the place. I'm not going to go into it in too much detail, other than what I've said already. But suffice to say that it's a sensible pattern. And at the heart of it is this tension. So we want all the good stuff that comes with a database, that ability to slice and dice data, but we don't particularly want to share our database with anyone else. We kind of know that, right? We all kind of, somebody says, oh, can I have access to your database? You're like, well, you're going to couple yourself to it. I'm not sure I really want you to do that. But we also need to share datasets in a sensible way. So we need some mechanism of doing it. Okay, so that's all pretty abstract. Let's try and take a little example. I'm going to keep using, as I said, this retail example. So how do we share data between services today? Well, that's really strange. Sorry, my picture looks different to that picture. So we have a web server, and we have an order service, a shipping service, and a customer service. And this is a very simple use case. So you can imagine this could be Amazon, where you're buying whatever you want to buy for Amazon, or maybe Apple, you're buying an iPad. And you have a web server, and the order service is going to manage the orders. The customer service is going to hold your customer information. And the shipping service is the thing that's going to basically make sure that that iPad makes it from the warehouse all the way over to your door. And you can then go off and enjoy your new Apple product. So let's say we do this with REST. If we do it with REST, then the web server would submit an order, and that will go to the order service. And the shipping service would expose an interface called ship order. And so the order service would call the shipping service. And then it would need to look up, it would need to know where to send your iPad to. So it would make a call to the customer service, get customer, get your address, and then the shipping process would continue. That's all pretty simple and intuitive. Why would I want anything else? Well, we can do this with an event-driven model. And this has some slightly different trade-offs involved, which are worth looking at. So again, we submit the order, but in a pure event-driven model, services don't actually talk to one another. And this is going to make sense in a minute. So in a pure event-driven model, we just talk events. So the order service actually raises an event that says, this order was created or requested. It actually doesn't know where it's going. It's going to the shipping service, but it doesn't know that. The shipping service decides to subscribe to these order events because it knows it's interested in them. And it continues to kind of off to do its processing because it's triggered by the notification that sits inside this event. On the other side, we have this customer service. And customer information is a little bit different because it's not about things that are happening now. It's about things that happened in the past. Like the last time you updated your customer information was probably the last time that you moved house, which was maybe a couple of years ago. So the customer event is not something that we can analyze in real time. But this kind of what these two sides of this particular problem expose are that really events have two hats. So an event is a notification. It's a call to action. Right? So this event happened, this business event happened, do you want to do something about it? But at the same time, inside that event is the information itself. So it's also state transfer. It's a way of moving data from one service to another. So in this case, you can actually use the customer service customer service can emit events, and those events can be collected over time inside a database inside the shipping service, which it could then query locally. So the core point here is that we can use either of these patterns, and we can mix them up as we see fit. So we can just use events for notification, in which case the order service comes in, it raises that event. The shipping service, which is very decoupled from the order service, because the order service doesn't know anything about the shipping service now, can just react to it. But it can still maybe make a REST call to look up your customer information directly to the customer service. Alternatively, we can use this events for replication process. We're still actually using the notification for the order service, but we can use the fact that events actually allow state to move to recreate the customer data set inside a database inside the shipping service. So we're actually using data sets for events for locality in this case. So this is useful for a few different reasons. One is it's actually going to make it much faster for the shipping service to potentially access that data, but also This is particularly useful if you're moving over, let's say, a different geography, or maybe you're running on a mobile phone, et cetera, et cetera. So events have two hats. On one side, they're notification, but on the other side, they can be used for data replication. So events are a key to scalable service ecosystems because they're actually decoupling the various different components inside them. And streaming is a tool set which allows you to deal with these events as they move. So let's take a quick look at what a streaming platform is. So it has a few different components. It has very simple interfaces with producers and consumers, which you can access in pretty much any language you can think of. We have a bunch of clients which we support in .NET and Go, et cetera, and there's a whole bunch of community ones for Kafka. There are connectors, which basically just allow you to get in and data in and out of a database, and then there's this stream processing API, which is literally just another API, but actually provides this very sort of much more functional interface for dealing with events and asynchronicity. So let's look at these quickly. We'll start with the log. So Kafka is a distributed log. That's actually the project I work on a day-to-day basis. And you can just think of it a bit like a messaging system. You can think of it being designed for that kind of use case that we talked about at the start, the one where we had the mobile phones emitting we want to store and process large numbers of small events. And the reason that use case works so well is that there is literally no bottleneck within the system. I can have a very, very big topic. I can shard data on the way in. It can be held on a whole bunch of different machines, where it's actually arranged as different queues, and we can arrange how data is sharded to arrange for strong ordering guarantees. And then many different consuming processes can share that one topic and process them at the same time. But there's some other quite nice properties. So the log can actually be used as a storage system. It can hold, you can put hundreds of terabytes into Kafka, no problem, even with compacted topics, which we're going to talk about in a minute. And one of the nice properties of this is that you can actually then rewind the log. So you can store these events, which holds, so you can imagine it's like every order that ever came in or every customer that ever came in, and you can rewind those events and replay. So that's really useful for this pattern called event sourcing. Sometimes, and we're going to be talking more about this idea of moving data around, and when you move data around, whole data sets around, you actually want to make them smaller. And the way you make it smaller is actually to make a log, which is every single change that ever happened, like a version history in Git. You want to collapse that just to the latest version, which basically looks like a database table. So you collapse it by key. That's what a compacted topic does. So it allows you to it will compact that data set down so you just have the latest value for each key, and it effectively would marry exactly with the database table. So that's the log. We have these connectors. If you've used ESBs before, this is actually a pretty similar pattern. It's a mechanism that allows you to get data out of a whole variety of different databases and get them very quickly into Kafka, or alternatively pull data out of Kafka and put it into pretty much any database that you choose. Please don't use Kafka like an ESB. You can, some people do, but it's typically not a great pattern. But these tools are useful nonetheless. And then finally, there's this idea of a streaming engine, which is in some ways a little bit harder to understand, but it's actually pretty useful. So there's a whole bunch of streaming engines out there. I'm going to talk about the one that literally ships with Kafka, which is called K-Streams. And this is basic. They're all roughly equivalent in many ways, although they obviously each have their own sweet spot. But effectively, they're a database engine for data that's moving. It allows you to basically manage data as events and actually, importantly, marry the concept of events and tables. So at a very high level, it's a continuously running query. The query that we started with, where we had a bunch of credit card, people using credit cards, authorization attempts, and we're constantly computing this query and outputting a result to another stream. That's a kind of canonical use case. So much like a database, you can do joins, you can create views, which is very useful for mapping whatever the data model is on the wire to your internal domain model before you start adding sort of further predicates or aggregates, etc. You can filter, you can aggregate, and all over you can add a window, which is how you deal with an infinite stream. It's how you reason about an infinite stream. But one of the things that I think most powerful about the streaming model, certainly the stateful stream processing engines, is their ability to deal with both streams and tables. And the reason that this is important is, whilst there are a lot of use cases which fit perfectly into pure streaming, most use cases are some kind of combination of the two. So you have like an event stream that you want to react to, but you also want to kind of look something up. Maybe you want to look up customer information whilst you're processing a stream of orders. So stream processing engines let you basically manage these two things. I can have a topic, which represents an infinite stream, and I can make a reference to a table as I go along. So the other nice thing about a stream processing engine is it handles asynchronicity. It does all this for you. So let's take a little example. Imagine we have two services, order service and payment service on the left-hand side. The order service, and they're both sort of submitting events. And you can imagine, like, when you create an order, like you're buying an iPad, a message would be sent to the order service, and you also make a message to the payment service. And there's probably some ordering around that, whichever way you did it. You probably create the payment, and then you create the order. But actually, you can't reason about that in an asynchronous system. They could turn up in any order, because the whole process is asynchronous. One might be delayed for whatever reason. You could get a race condition. So if we want to write a very simple program that just sends the user an email to say, congratulations, you bought a new iPad, it cost you this much, et cetera, we need to join these two things together. And the way that works is the emailer can basically subscribe using the Kafka Streams API or whatever you're using, can subscribe to these two different streams. And what the stream processing API will actually do is it will buffer for some amount of time that you configure. And it will buffer so that you can do that join and not have to worry about which event came first. It handles that asynchronicity for you. So when the payment and the order event are both present, then your email code will be triggered, and you can send the email. So that's kind of how you buffer and join streams. It's very simple. So you can do this in KSQL. If you're off the JVM, if you're on the JVM, you can use the Kafka Streams API. It's basically a few lines of code. Create a stream. The names in quotes are the topic names, and then the join is just obviously a couple of lines, and we're just calling that email service, that email function to send an email. But this table thing, as I said, is pretty interesting. And what is a table really? Well, firstly, let's think of the use case. So let's add the customer service in. So let's say the emailer needs to know where to send your email. Your email is on your customer information, which is located inside the customer service. And we wanted to kind of do this in a streaming way. What we'd actually do is create a table of customers inside our emailer. And what a table is it's actually the same thing. It's the event stream, which is held inside Kafka. It's materialized locally. But instead of just retaining maybe 5 minutes of data, you retain the whole data set. And you actually use one of those compacted topics we talked about earlier to do this, so you don't have to move too much data. And often also filter it. So a table is really just a stream with infinite retention. Again, very simple to do. It's one line of code. Instead of builder.stream, it's builder.table, and the API deals with all the rest of it. And then when we do our join, it's effectively exactly the same thing again. We use a tuple this time instead of a key value, but effectively we're just going to the emailer will be called every time the order, the payment, and the customer information is all available. So what we're really doing is materializing a kind of view, a streaming view, which our code is reacting to. So we can also do this, I said, with KSQL. With KSQL, you basically have a separation. So the KSQL engine, you just run as a separate node or a sidecar, and that does the computation, creates an output of a stream, which would then drive the emailer, and I might write the emailer in Node or C# or whatever I like. So because obviously this has got a background in stream processing, we can obviously scale these things out. We can have high availability of our services. If one goes down, the other one's just going to naturally take over. All of that good stuff just falls out of the box. So really, if we step back a little bit, stream processing is about kind of two things. It's about processing data incrementally, reacting to events. So that's the notification hat of an event. But it's also about moving data to wherever it's needed. We have that tool also. And that's really that data replication hat that you get with events. So we can localize the data set so we can process it quickly, or actually also, as we'll see, because that gives us autonomy, which allows us to evolve independently of the rest of the ecosystem. So let's walk through some steps to building a more realistic, or slightly more realistic streaming ecosystem with these tools. So there's 10 steps here to building this little ecosystem. The first one is basically to take responsibility for the past. It's actually pretty unusual that you see someone start a completely greenfield project. Normally, if you're completely greenfield, you're a startup, in which case you should probably be building a monolith anyway, because you need to get something out the door quickly. And microservices and other distributed patterns do come at a cost. So you'll typically have something. If you work in a big company, there'll be some legacy somewhere. Let's start with a very simple monolithic application, 3 tiers. And let's say we evolve forwards. So we're going to split out an order service. This is kind of our path to try and extend our architecture so that it has different components which are independently deployable. So one of the things we kind of want to aim for in this model is having an asynchronous core, and we want to have synchronous interfaces as edge services. So internally, we're going to raise events rather than talking directly to services because it allows the different services to remain decoupled. So instead of talking directly to the order service, we can make a request through a broker. So the web server could send an order received event, and then that gets picked up by the order service. And then the order service would then validate the order and then create an order validated event, which would be picked up back by the web server. Next, we can use the connects interface, typically using CDC, although we don't have to evolve away from some legacy system. So really, this tends to be pretty useful because you typically have a database which is already filled with useful information, and a lot of that you just need to get into this stream processing pattern. So we can attach, so we can attach a connect interface onto the back of the database. I mentioned that term CDC. There are a number of connectors which implement this thing called change data capture, and there are a number which just basically go through a front door, or for some of the NoSQL databases do something that's in between. But CDC is actually a really efficient way of getting data out of a database. So a database at its core has a transaction log, which records basically, it's very similar to a log in Kafka. It records every single change that it ever does. And CDC basically just tails that log and turns it into events. So when you're picking a seam, so typically when you have a legacy application, you need to pick a sensible seam where you can kind of carve the workflow away. I actually see people do it in the data layer quite a lot. But actually a really good way to do this, which a lot of people use, is just to pick a seam that's inside the database itself. So you literally just turn a database table into an event stream. So in this case, we've pulled the data set of products, which maybe we don't want to build a service for right now. We're quite happy maintaining products inside the legacy application. We've pulled that into Kafka, and then we can start to use that product data set in our evolving ecosystem. So next, we want to make use of schemas. Schemas are really important where you have independently deployable services. So if you just have one deployable unit, it's just one app, you can often get away without using these. But really, schemas are the API for an event-driven system. They're the thing that describe the contract. So if I have an ecosystem where I have independently deployable services, then I need some way to kind of reason about this contract or this event. So you want to use some kind of schema to describe the messages that flow and really to allow you to kind of evolve that over time. So if I attach a new service to this ecosystem, I want to know that that data set is always going to be backwardly compatible. So Kafka ships with a thing called the Schema Registry in the Confluent version, in the Confluent distribution, or you can use your own. So use schemas. Next is Rice is applying the single writer principle. So the reason you need to do this is that in this kind of model, you have no global consistency point. We didn't use a big shared database, which provides a global consistency point. So we need some other way to reason about consistency and ordering. And a good way to do this is to basically assign responsibility for effectively what effectively is a mutation, logically it's a mutation, to a single service. So the order service in this case is responsible for progressing the workflow of an order forwards in time. So no one else is able to do that writing. And this gives us what is effectively a kind of causal consistency model. So as the service on the left creates an event, it kind of flows through Kafka, the validation occurs inside the order service creates a new record so that it's validated, and maybe that flows out to this email service. The important point here is that actually each of these services is separated in time. They're actually disconnected in time, but the event flow, because it is record by record in an ordered queue, is each of these services basically sees a consistent view of changes as they happen. So this gives an element of slack in the system, but at the same time allows you to manage consistency. And we'll give an example of that in a little bit. So the single writer does a couple of things. Firstly, it creates a local consistency point in the absence of global consistency. Also, it actually makes it much easier to do things like change schemas later. Like if you have 7 different services changing a particular event stream, then it's actually quite hard to upgrade that schema because each of them has to kind of go as a single. The upgrade tends to have to happen as a single release. So 6, we can store data sets inside the log. So, as I said, Kafka can basically store data indefinitely, and we can use these compacted topics to create a more like tabular-like view. So what that really means is that we can externalize these data sets. These are shared data sets which different services need to use inside the log. And that gives us nice pluggability to the architecture. So let's say we want to build a new service. We're doing repricing. So we might make use of an existing event stream, and we might also need to make reference to the product data set, and we can join these two things together inside our new repricing service, and obviously, because it's an event-driven model, we can just plug this right in. So in this case, the event stream would be something we would react to, but the product set would be an entire data set which we would just materialize locally, either in a database or inside the stream processing engine, as we see fit. So it's very easy to plug new services into this kind of model. This is kind of like a real advantage to this type of approach. And then we can evolve this forward, so we start to create this kind of single source of truth. So again, we don't really have a shared database. We don't have any shared functionality for analyzing data. We're really just sharing these data sets as streams, either as things that we react to or as data sets which we can take in their entirety. But how do you actually query a log? You obviously do need to do these, to run queries against the data that stores there. It's stored in there. Well, that's where we actually start moving data to code. Now this should be a little bit unintuitive. For a long time, we have not done this. For a long time, we have always moved code to data, and that made a lot of sense, right? Data's heavy, code's light. We should obviously move code to data. That's kind of the database mantra. One of the problems with taking that mantra is that if you continue doing it forever, you would basically build all of your systems inside a database. That would be the logical conclusion, right? We'd have a big ecosystem made by Oracle, and we would all write our code inside that. And typically, we don't want to do that. Other than the fact that you probably don't want to write business code in SQL, even if you did, you probably wouldn't want to maintain it inside a database because it would be really hard to manage that. Right? You need to be able to manage code yourself so that you have the freedom to pick the tools that you want to use and have independent deployment cycles. So one of the nice things about this streaming approach is it gives you this flexibility. You can, of course, move code to data, but you can also move data to code. So let's see how that fits into our little evolving ecosystem. So in this case, we might have the stock information, so what items we have in the warehouse. And the order service is going to need to do some validation. One of the things it's going to have to do is validate to work out whether or not there are enough iPads in stock for you to fulfill your order. So we can materialize that data set inside the order service so that it can query it locally. And importantly, this gives the order service autonomy over its data set so it can manage its own release cycle. The second trick is because the data set's actually stored inside Kafka, we don't need to absorb the whole thing into the order service. Right? We can actually only take the data that we need. This is actually pretty useful. So to validate whether you have enough iPads in stock, you need two pieces of information. You need to know the product code of the iPad, and you need to know how many items there are in the warehouse. So you've basically got a key and what is effectively an integer, or if you're Amazon, it's probably a long. So this idea of data movement allows us to optimize for locality, but it also gives our services autonomy because they're internalizing that data set where they have control. But on the other side, we need to also be realistic about this. Actually, moving data over the network isn't typically the bottleneck. You've got a distributed log behind you. You can move data sets really fast. You can distribute your services over many different machines. The thing that tends to be the limiting point is indexing. So the cost of indexing is actually relatively high. So if you use a database which has got uses a large number of indexes, like something like Elasticsearch is pretty slow to update, that tends to be the limiting factor. So we can get around this by either leaving indexes in memory, or scaling out over multiple machines, or by this trick of keeping data sets relatively focused, because we can always go back and get more if we need it. So using the log as a database, this basically means event sourcing, but we can actually use, so we pulled this stock data set into the order service, but if the order service just wants to say lightweight, and doesn't actually want to have an external database, we can actually use Kafka as a kind of database. So in this case, let's say the order service, it knows what's in the warehouse. It also needs to reserve an iPad. Right, so there's a bunch of iPads in the warehouse. That number would go down as iPads were shipped out. But as soon as somebody creates an order and that order is validated, we need to record that iPad is effectively reserved for the duration of the order. So we need to kind of write some intermediary state. So we can do that literally just by writing. We actually write to the table. That's actually the way that you do it. You create a table, and you write to that table, and it will be backed up in Kafka. Or you could obviously just write directly to the stream if you preferred. Now, if you do this, then what actually happens is the data set is stored in Kafka, and when the order service starts, it will load that data set that we've created of each stock that we've reserved into the order service. And it actually, Kafka Streams implements a thing called a state store, which is basically just, it's a type of database of sorts, but really it's much simpler. It's a disk resident hash table, which allows you to basically store these data sets and access them very quickly. So because moving data around to two services is a relatively difficult thing to do, and one of the things we need to do is make sure that we can do this in a reliable way. And stream processing engines ship with a bunch of features which basically make this problem practical, because they're really optimized to solve this problem. So there's a few things. There's standby replicas, which effectively means that you have a replica of any data set in one instance of a service in a secondary node, and they effectively run it as a highly available pair, or as many as you need. And if one goes down, the work events will immediately fall over to the other one, and the state will be there ready for you to use. Likewise, there's disk checkpoints, which is exactly what you might think. It's journeying this data to disk. If for some reason a service goes down and comes back up again, it can access the disk checkpoint. It'll be a little bit behind, so it would just catch up from the log to get itself back to a consistent state. And we talked earlier about compacted topics, which are really about reducing the amount of data that we need to move around. So nearly there. Number 9 is using transactions to tie it all together. So transactions are actually pretty interesting in Kafka, I think. They're in some ways a bit like a transaction in a database, but in some ways not. So the output's kind of the same. It's about having automaticity. So let's say we're going to keep looking at that orders service. We have that order requested event which comes in. Somebody orders an iPad. When that happens, we actually need to do 3 things. And we need to do those 3 things atomically. Firstly, we need to commit our offset. That's an internal Kafka thing. But that basically ensures that you don't get the event again. It's just saying, I've got that event, and I'm done with it. Thank you very much. Then we need to do 2 other things. We need to once the order is validated, we would create the order validated event. But we also want to record that the iPad has been reserved. And each of these are going to be basically writes to different topics. So this is actually the write of an event, which we're using as an event stream. This is actually much more like a write to a database, because it's internal to our service. And all of these 3 things we can wrap up in a transaction. This just happens automatically if you use Kafka Streams. You just enable transactions, and it's all atomic. And obviously, because it's a stream processing system, it's designed to run this at scale. So this is not like an XA transaction, which sits for several milliseconds. This will work at big data volume, no problem. So transactions allow us to tie these kind of business operations inside this service, where we've centralized these consistency concerns using the single writer principle, and allows us to update various different pieces of state and events atomically. It's quite a powerful idea. And finally, we bridge this synchronous-asynchronous divide in a streaming ecosystem. So I'm not going to... This is actually a more complicated version of that one service we've been talking about so far. I'm just going to talk about it briefly. So what we have here is on the left-hand side, we have a very simple REST interface where we can post an order and we can request an order to get it back by its key. And what we're actually implementing, the pattern inside here, is CQRS. So as soon as that order gets created, the order event is written to Kafka and split out into a set of different workflows. So we have 3 validation engines: a fraud service, an order service, and an inventory service. This was the one that we were talking about a lot today. And each of those can run in parallel and can perform its appropriate validation, creates another event which goes back to the order service. So this is all asynchronous. This effectively dams those streams. These streams are all flowing constantly. The order service here, the CQRS, the query side of CQRS, is effectively damming the stream and creating something that we can query, and joins the whole thing together. So that's kind of a very simple example of how we can build a streaming ecosystem which bridges a request-response synchronous interface with something which is effectively asynchronous. So it's asynchronous core and a synchronous interface. I should also say that so the code for this is online. I have a link for it at the end, and there's a post that describes how it all works. But this is a sort of a test case, as it were, for how you can build an ecosystem, this type of ecosystem. There's a number of systems I've seen that use this type of pattern. Definitely a pattern which is very scalable, right? So you probably wouldn't need to use this kind of pattern for an order service if you were just building a small website. But if you're working with something that requires more scale, this is the kind of pattern that you would use. But what's really more important about this is it kind of sows the seed for how you build more complicated ecosystems. And the answer to, as when you actually come to design these things, the question you're asking is, what needs to actually scale and what needs to be independently deployable? So in this instance, it was actually very easy for these different services to be independently deployable. Your question would be for yourself is, do I need that? So what this model really is a async core model. So at the core of the system is asynchronous, and we have synchronous interfaces on the boundaries. And as we scale that out and keep these historical event streams, the event streams become a kind of system of record. So this is this idea of a database inside out. Anyone seen Martin Kleppmann's talk on a database inside out? It's a really good talk. I think there's a link for it in the associated blog post. But the interesting thing about this is the stream actually behaves a lot like a database in that it stores data sets for you, but each of our services is able to embed the processing that it needs to slice and dice those streams. So each of these services share a set of data set, have a shared data set, but they own how that data is sliced and diced, which really brings us back to that data dichotomy. It allows us to share data, but retain control over how it's sliced and diced. So it's a bit like a database, but like inside out. And obviously we can scale this out. As we scale this out, we can add more services. We can span different geographies. We might have a set of services running in New York and London and Tokyo, etc. We can build these more globally disconnected ecosystems. So, what do we have? At a high level, for me, architecture actually has little to do with writing something on a whiteboard. It's quite easy to design a system on a whiteboard. It's much harder to work out how that system's going to evolve over time. Actually, because it's not just a technical problem, it's got a lot to do with people. So, for me, the essence of a good design is its ability to evolve over time. And actually, that's as true for your software as it is for a system architecture. So, request-driven interfaces typically isn't enough. Not for a big ecosystem. We want to embrace asynchronicity, often because we actually have business processes which themselves are asynchronous, like shipping an item to your door. But also because synchronous interfaces, particularly when they get deep, actually provide a lot of coupling. There's almost like a law of Demeter, if you've come across that, for the way that systems interact. So we want to leverage the duality of events, both the notification as well as the ability to move data from process to process. And we can use a streaming toolset to help us to solve those kinds of problems, to deal with asynchronicity, to actually slice and dice data as it moves. So remember the data dichotomy? Data systems are really about exposing data, and services are about hiding it. So that means we want all the good stuff that we get with a database, but we don't want to share that database with anyone else, but we do want to share the data sets that they hold. So we want to be able to share the data sets, but we want to manage the slicing and dicing ourselves and have autonomy over how that evolves over time and when that changes. So for event-driven services, we want to broadcast events, retain them in a log, compose a system as a set of streaming functions, and then recast that event stream into a view when we need to query it. And that's the essence of services built on this kind of streaming platform. And that's all I had to say. Thanks very much for listening. Again, my name is Ben Stopford. If you want to find out more, the slides are available
on my website. There's a blog series on the Confluent blog, and there's code for those code examples in that URL. And yeah, you can find all this on my website. If anyone has any questions, I'm not sure if we have a microphone here, but I'd be happy to take them now. I'd also be happy to answer anything that people have, any questions people have at the end, and we'll catch me around as you see fit.